All right, guys. Yeah, good morning. Good morning, guys, everybody. I'm disappointed with the attendance. So this is week 10. So we are in week 10 right now. So let me see if this works. Okay, guys, we are in week 10 right now, so we got 2 more weeks of lessons to go. So this week I'll talk about hypothesis testing. Next week we will do examples on hypothesis testing, and the week after will be revision week to prepare you for the exam. Right? Okay. And few announcements. The quiz number 9 is due by 11 o'clock today. So if you haven't done this quiz, please do so before 11. Okay, as usual, I will send you an email with the correct answer and how it was obtained. Okay? The exam, I'm sure you know when the exam is going to be. It's on the 25th of May. The formulas that you need to remember for the exam are here. These are the only, I think many people ask me this question. These are the only formulas you need to remember, and when I say remember, you need to remember them by heart, right? So you cannot take any piece of papers to the exam hall, right? So you need to remember only just a page of formulas. These formulas here, you will need to remember them. Okay, and so the exam will be marked by myself. I mean, everything will be marked by myself. So you should get to know your results within a month or so of the exam, right? And likewise, the R coursework, which is due on the 20th of May, will be marked by myself, and you should get to know your mark within about a few days after the deadline. So you should get to know your mark within about 2 or 3 days. Okay, so this is the R coursework is marked out of 10, and a few people ask me, like, the report that you write, you can use LaTeX or Word or any other software that you know of. But when you submit your report through Blackboard, please upload the PDF version, right? So whatever software you use, just upload the PDF version of your report. Okay? Is that clear, guys? Yeah or no? You guys okay? Yeah. You can. I mean, in your report, you should include your R commands. You can include the figures, the explanation of the figures, and so on, right? As long as it's within 5 pages, it's fine with me. Because I've got to mark like nearly 400 papers, well, over 400 reports. So, I mean, if you write a lot more than 5 pages, then it's too much for me to mark, as you can imagine, right? Okay, and so let's go back to week 10. So we are currently in week 10, right? So these are the contents for week 10. There were 4 tutorials that took place this week because of the bank holiday on Monday. We did not have classes, so we did not have tutorials on Monday. So there were only 4 tutorials that took place, and the attendance was very poor as usual. So if you haven't been to your tutorials, if you have not been to your tutorials, please listen to one of these videos, or you can also listen to the the full video giving the full solutions to all the questions, which is this one here, right? So, okay, and you can also look at the typed solutions and also look at the handwritten solutions for all the questions. Okay? All right, so what I'm going to do today, as usual, is to go through these 1, 2, 3 videos. There's a video on test of hypothesis, one on one sample test, and one on 2 sample test. Oh yeah, one other thing I forgot to say. Yeah, a few people ask me, like, what's the content of the exam is going to be? The exam will be very similar to the past years. Some people did not even know, like, this website contains the past year's exam papers. So you can see the previous exam papers, 1, 2, 3, 4, 5, 6, 7. So the last 7 years exam papers and the solutions are contained in this website. Right? That should be enough for you to practice, right? That should be enough practice for you. And the format of the exam will be very similar to let me show. Yeah, it will be very similar to the last 4 years. That is this one, this, and this one. So the format of the exam will be similar to the last 4 years exam papers, right? And as far as the content of the exam is concerned, it's pretty much everything that we covered in this course, except for 2 sample confidence interval, 2 sample test of hypothesis, continuity correction, which I did not talk about, and normal approximation, which I also did not talk about in the course. So normal approximation, continuity correction, 2 sample tests, 2 sample confidence intervals will not be examinable for the exam, right? Okay, everything else we did in the course will be examinable, right? Is that clear, guys, or no? Yeah, right. Okay. Now, just to make sure that you know that this website does contain the past exam papers and the solution for the past 7 years. So please, there should be enough material for you to practice. But anyway, we will come to that later, like in 2 weeks' time. But for the moment, let's look at what we're going to do this week. So I'm going to go through these 3 things here, starting with test of hypothesis. So the test of hypothesis is, some of you may know, like there are 4 different things. Oh, sorry, no, there are 6 different things when it comes to testing hypothesis. There are 6 different elements. The first element is known as the null hypothesis. Right? You can also, if you want, you can, let me put the middle one also, you can see it more clearly. The first one is known as the null hypothesis, right? So that's the hypothesis that's to be tested. So for example, it could be something like the average weight of men in the UK is, say, 70 kg, right? The alternative hypothesis is sometimes known as the research hypothesis, right? So that can take 3 different forms. So for example, the average weight is less than 70 kg, or greater than 70 kg, or not equal to 70 kg, right? So those are 3 examples of, or 3 typical examples of an alternative hypothesis, right? A test statistic is a function of the data. So x1 to xn is a data set, and t is a function of the data. And this function is used to determine whether to accept or reject the null hypothesis, right? So if we accept the null hypothesis, then we reject the alternative hypothesis. If we reject the null hypothesis, then we accept the alternative hypothesis. You know what I'm saying? Yeah? So that's the test statistic denoted by this. Now, the rejection rule for the null hypothesis can take one of the forms. Either the test statistic is greater than a constant k or less than a constant k, right? Or some other form similar to this, right? So this is the rule that is used to determine whether to accept or reject the null hypothesis, right? And element number 5 is the rejection region. It's basically the set of all data sets, a set of all numerations of the data that belong to the sample space S. I'm sure you know what a sample space is from probability 1, such that the rejection rule holds. So it's a set of all enumerations of the data belonging to the sample space such that the rejection rule is satisfied, right? That's the rejection. That's the rejection region. And finally, the number 6. Number 6 is the acceptance region. So the acceptance region is the set of all enumerations of the data such that rejection region is not satisfied, right? So once again, S is the sample space, right? So these are, for any problem on test of hypothesis, we'll have these 4 different elements: null hypothesis, alternative hypothesis, test statistic, rejection rule, and the rejection rule, and the rejection region, and the acceptance region, right? So now, okay, let's come to this. Let's come to this. Now, in real life, as I explained before, you can either reject the null hypothesis or accept the null hypothesis. So there are 2 possible outcomes that you can have. Either you reject or accept, right? But if you look at the state of the nature, which we have no control over because we are only human, right? The nature can be either that H0 is false or H0 is true, right? I mean, only God, whoever your God is, will know whether H0 is false or H0 is true, right? Okay? So there are 4 possible outcomes. There are 4 possible outcomes. If H0 is true, you might as well reject the null hypothesis, which is not an outcome that you want. You don't want, okay? You don't want this happening, but it can happen because we are only human beings, right? When H0 is true, we might decide to reject it. That's a possible outcome. And when H0 is true, we might accept it. That's a possible outcome. That's the right outcome, right? When H0 is false, we might reject the null hypothesis, which is also a possible outcome, and it's a correct outcome. And finally, when H0 is false, you might decide to accept it, which is again a possible outcome, but that's not the outcome that we want, right? But it can happen, right? It can happen, right? So there are 4 possible outcomes. Out of the 2 outcomes, outcomes that we like, and the 2 remaining outcomes are outcomes that we do not want, but that can still happen. Okay? And this outcome is known as the type 1 error, and this is known as the type 2 error. So just to summarize in words, type 1 error is that of rejecting H0 when H0 is true, and type 2 error is that of accepting H0 when H0 is false. So in test of hypothesis, what we try to do is we try to create a test so that the probability of type 1 and type 2 errors are minimized, right? I mean, it is impossible to eliminate the probability of type 1 error and the probability of type 2 error. But you can only try to minimize the probabilities of type 1 and type 2 errors. That's all we can do as statisticians. Okay? All right, now just for notation, for notation's sake, I will denote alpha as the probability of type 1 error, beta as the probability of type 2 error, And alpha also denotes is also known as the significance level of the test, right? That's this notation here, right? All right, typically alpha is taken to be 0.05. That's the typical value for alpha, right? And we also try to minimize the value for beta as much as possible, right? So that's the first video. The second video, all right, let's go. Are you okay with this one? Any questions? This is the second video. I hope you watch this one. This is on one sample test, right? There are 4 different tests. The first one is for testing for population mean when the population variance is known. The second is for testing for population mean when the population variance is unknown. The third is for testing for population standard deviation. And the fourth is for testing for population proportion, right? So these are the 4 tests I'm going to talk about. In each case, I'm going to give you a set of rules. So these are the rules for testing for population mean when the population variance is known. So for example, if you want to test that the population mean is equal to constant mu sub 0 versus it's not equal to constant, this is the rule. This is the rule for rejecting the null hypothesis. And for this is the rule. And for this is the rule, right? You may wonder where these rules are coming from. You may wonder why this, I mean, it's not part of this course it's not part of this course for me to teach you how these rules were obtained, right? But when you go to year 2, there is a course called Statistical Methods, taught by Professor Corbini and Strymer, right? You may want to take that course, and in that course you will learn how these rules were derived, right? Okay, you follow me? So this, for the moment, for this course, you just need to know these rules. Just it. I don't expect you to know how to derive them, which is beyond the scope of this course, right? Okay. All right. So these are tests for population mean when population variance is known, and these are tests for population mean when the population variance is unknown. You see the difference here. The difference is that we are using S instead of sigma. So sigma here is the population standard deviation, which is assumed to be known, but here we are using S, which is the sample standard deviation, and defined to be this, right? All right, and also we are using the percentiles of the t distribution, and not the percentiles of the standard normal, which is Z, right? The third one is testing for population standard deviation. So these are the 3 possible tests, and the rejection rules are these ones here. So here we are using the percentiles of the chi-square distribution, and you will get, in the exam, you will get tables for the normal, the t, and the chi-square. So you should just please make sure that you know how to read them. Okay, please know how to read the percentiles of standard normal, percentiles of student t, and the percentile of chi-squared, right? Okay. These rules here involve percentiles of chi-squared. And the fourth and the last one, here we are testing for proportion. So we have a random sample from a Bernoulli with P, like, so for example, you could test whether the proportion of smokers in the UK is say 0.3 or not equal to 0.3, right? So you're assuming 30% of the population smokes, and the remaining 70 do not, right? So that's a possible example of a hypothesis involving proportions, right? And these are the rules that you will use, all right? Here, x bar is the sample proportion, not sample mean. So whenever you have a question on sample proportions, X bar denotes the sample proportion, not the sample mean, right? Okay, you follow? I mean, I think we did some like examples like that in the tutorials this week where you had proportions and X bar denotes the sample proportion, right? So these are the 4 tests. So once again, these are tests on population proportion, these are tests on population standard deviation, these are tests on population mean when the population variances are known, and these are tests on population mean when the population variance is known, right? Okay, so that's the second video. The third video I asked you to watch is this one here, 2 sample test. I mean, this will not be examinable, but I would still like you to know, right? At least for the examples, at least for the tutorial next week. I mean, there will be tutorials. By the way, there will be tutorials next week. It will be based on sheet number 11, right? The example sheet number 11, right? But the week after next week, there will not be. Well, I'll have to check just a minute. All right, let me check whether the week after next week, which is week 12, there will be a tutorial too, right? There will be a tutorial week after next week too, right? Okay, so I just wanted to make sure, right? All right, 2 sample tests. Once again, there are 4 different 2 sample tests, right? The first one is for testing equality of population means and the population variances are known. The second is testing for equality of population means when the population variances are unknown but equal. The third is testing for equality of population means when the population variances are unknown and not equal. And finally, testing for equality of population proportion. So let's start with the first one. So here you have 2 random samples from 2 normal populations. We are assuming that the population variances are known, right? In this case, these are the 3 different hypotheses that you have, and these are the corresponding rejection rules. So once again, I mean, the derivations you don't need to know, but you will learn them in year 2 in the statistical methods course, right? Okay. This is 2. This is the second. Here we are testing equality of population means when the population variances are unknown but equal, right? So here, instead of the Z percentiles, we are using the T percentiles, and instead of the population variances, which I assume to be known here, we are using the SP squared, which is the pooled sample variance, and is defined to be this, right? This is the pooled sample variance, right? And the third set of tests is this one, right? So here we are testing for equality of population means when the variances are unknown and not equal. So the corresponding rejection rules are this one, and this one, where A is defined by this complicated formula, right? Sx squared is the sample variance for the first one, the Sy squared is the second sample variance. And finally, testing for equality of population proportions, right? So here, these are the 3 different hypotheses, and the corresponding rejection rules are these ones, right? So testing for equality of proportions, I mean, it comes naturally. Like, so for example, if you take 2 different cities in the UK and you want to see if the proportion of smokers in Manchester is the same as the proportion of smokers in London, right? Then you have a case of testing for equality of proportions, right? Okay, you follow what I'm saying, right? You draw a random sample from Manchester, say 100 people, and see how many of them are smokers, and the same thing for London. And then you have a testing, you test whether the proportions are the same or not equal, right? So you can use one of these tests to perform the test, right? All right. All right. So I've gone through the three videos. Now what I'm going to do in the remaining time, as usual, is to do as many examples as possible. Unless you have, do you have any questions on the three things I asked you to watch? Come on, guys, talk to me. Any questions? Seth, you all right? Okay. So let's start doing some examples, guys. So example 1. I didn't do any examples on this. So suppose x is a Bernoulli random variable with parameter p. Consider testing Right. So this is a question on the kind of stuff that we learned today, right? So we have a data point, a single data point that is Bernoulli with parameter p. I assume you know what a Bernoulli is, right? You probably, yeah. And we are trying to test the hypothesis that p is the probability is half versus not equal to half. And the rejection rule is that if x is equal to 1. And the question is to find alpha and beta. Now, remember, alpha is the probability of type 1 error. So alpha is defined as the probability of which is what? I mean, the type 1 error occurs like is rejecting H0 when H0 is true. So it's the probability of reject H0 when H0 is true. Right? Now we reject H0 if x equal to 1 and H0 is true if p equal to half. So what do you think this is? Come on, guys, talk to me. What is the probability that x equal to 1 when x is Bernoulli? Let me take you through this. Do you remember the Bernoulli variable? The Bernoulli variable is defined as taking two values, x equal to 1 if the outcome is a success, 0 if the outcome is a failure. So the probability x equal to 1 is p, and the probability that x equal to 0 is 1 minus p. So what would this be? This would be half, right? You follow me? Huh? Or no? Okay, right? Are you guys okay with this or no? Some of you seem lost. Yeah? And beta is the probability of type 2 error. Which is, you should go back to to this. The probability of type 2 error is the probability of accepting the null hypothesis when H0 is false. So this is the probability of accepting H0 when P is not equal to half, right? Because H0 false means that P cannot be, H1 must be true, right? So which is this. Now this is 1 minus the probability of rejecting H0. Yeah, by the negation, by the probability of rejecting H0 is the probability that x equals to 1 and P is not equal to half, right? Okay, now if you go to the Bernoulli, this would be 1 minus P not equal to half. All right, so this is the answer for beta, and this is the answer for alpha. Do you get it or not? Talk to me, guys. Are you okay with this or not? Yeah? All right, so that's example 1. Let's do the next one. Are you guys okay with this example or not? If you're not okay, give a shout. Feel free to. You all right? All right, good. All right, next example 2. I mean, you will get a question on. You will get a question on one sample test of hypothesis. So the more examples that we do, the better for you guys. All right, so here we have a random sample from a Poisson distribution with parameter lambda, and we want to test if lambda equal to 1 versus not equal to 1. And once, sorry, this should be, did I say n? It should be 1, guys, sorry. It should be 1, not n. And the rejection rule is that if x bar is greater than 1, the question is to find alpha and beta. So let's start with alpha, which is the probability of type 1 error. So this is the probability of rejecting right, and this is the probability that x bar is greater than 1 when lambda is equal to 1, right? Now x bar, remember x bar is the sample mean, so which means we can write it as 1 over n times the sum okay. You follow me? Yeah. Now if you take the n to the right hand side, this will be the probability that the sum of xi is greater than n. Okay. Now, let me ask you, what do you know about the Poisson distribution? This is the Poisson distribution. I'm sure you've seen this before in your probability 1. Yeah? What do you know about the Poisson distribution? Now, do you know the property that if you have in IID Poisson, then the sum is also Poisson? Do you know that or not? Did you learn that in probability 1? Like if you have IID variables that are Poisson, then the sum this is using the fact that if you have independent and identical Poisson variables, then the sum is also a Poisson variable, with the rate parameter being this, the rate parameter becoming lambda times n, right? Okay, right? So now what you have here, because we are conditioning on lambda equal to 1, we can write this as the probability that we don't need the conditioning anymore, because the condition, we have taken account of the conditioning that lambda equal to 1. So this lambda n becomes n, right? Right? So this is the probability that a Poisson variable with parameter n, if it is, because a Poisson variable can only take integer values, if it is strictly greater than n, right? If it is strictly greater than n, it must be greater than or equal to n plus 1. Yeah? So this is the sum sorry, this is probability, what am I saying? All right? You follow the step from this to this, because if it is strictly greater than n, and Poisson being an integer valued random variable, if it is strictly greater than n, it must take values from n plus 1, n plus 2, etc. Right? And now I'm going to use the right, so this is the answer for alpha, right? Is that clear to all of you or not? Anyone confused by this or not? Come on, guys, give a shout. Feel free to shout at me if it's not clear to you guys. Now, beta is the probability of type 2 error. Which is the probability of accepting the null hypothesis when H1 is true, which H1 is true, right? So this is the probability that, so accepting, I mean the rule for rejecting was x bar greater than 1. So the rule for accepting would be that x bar less than or equal to 1, right? You follow me? And H1 is true if lambda is not equal to 1. Yeah? Okay. Now, I hope you are following me. So this is the probability that x bar is the sample mean. Less than or equal to 1 when lambda is not equal to 1. Right, now take the n to the right-hand side of the inequality, then this becomes yeah. All right, now I'm going to use the same property I did, right? That is, the sum of IID Poisson variables is also Poisson, right? So this guy here becomes the probability that a Poisson variable with parameter lambda n is less than equal to n, given lambda is not equal to 1, right? Okay, so this is the probability that a Poisson variable with parameter lambda n is less than equal to n, but point out that lambda is not equal to 1, right? Now this you can write as the sum I from 0 to n of the probability, because remember the Poisson can take any value from 0 to infinity, right? So the lower limit is 0, not 1. Okay, so yeah, lambda not equal to 1. Okay, and finally, excuse me, so this will become the sum I from 0 to n e of minus lambda, sorry, the rate parameter to the power I divided by I factorial. All right, and lambda not equal to 1. All right, so this is the formula for beta. So we're done. Are you guys okay with this or not? Come on, guys, talk to me. Are you okay with this example or not? All right, the example number 3. So I hope you're okay. I will scan the stuff and example 3. So H1. Right. So here we have a random sample from a continuous distribution, namely the normal distribution, and we are testing mu. Mu is the population mean equal to 0. It's not equal to 0, and the rejection rule is this one. We want to find alpha and beta, right? Right. Let's try to find alpha first, which is the probability of rejecting H0 when H0 is true. So this is the probability that X bar absolute value is greater than 1 when mu is equal to 0. Right? Now, do you know how to deal with absolute signs? I mean, you must have done that in your analysis course or something, right? Like if you have, if X bar is greater than 1, it means that either X bar is greater than 1 or X bar is less than minus 1. You know this, right? Or don't you know this? Like if the absolute value of something is greater than 1, that means either this happening or this happening, right? Okay? So because they are mutually exclusive events, you can write this as right? Okay, now what I'm going to do is I'm going to do the following. You will see in a minute why I'm doing this, but let me first do it anyway. Can you, okay, let me ask you a question. What is the distribution of this? Can you figure out what the distribution of that is from the stuff that we learned ages ago? Let me show you where it comes from. You should look at this, right? One of the properties that we learned is this one here. Right, that if you have a random sample from a normal distribution, then the sample mean is also normal with these parameters, mu and sigma squared by n. Now, so using this property number 6, can you tell me what the distribution of these two are? Come on, guys, talk to me. I'm using this property number 6. So using this property number 6, property 6 of the normal distribution, right? You can see that what you have there is standard normal greater than root of n, right? And what you have here is the probability a standard normal is less than minus root of n, right? All right, so this is the first one. You can write it as 1 minus the probability that n01 is less than or equal to root of n plus the probability that n01 is less than minus root of n, right? So the final answer is phi at root of n plus phi at minus root of n. So this is the answer for alpha, the probability of type 1 error. Is that clear or not? Or are you lost? Some of you lost or no? I use property number 6. Sorry, where am I here? I use property number 6 from the normal distribution, right, to go from this line to this line here, which is the crucial step, right? All right, and so that's alpha. Now beta, let me do it quickly because I only got a couple of minutes left. So beta is the probability of type 2 error, which is the probability of accepting H0 when H1 is true. Right, so this is the probability that is less than or equal to 1 when mu is not equal to 0, right? So now this you can write as, if you know stuff from your analysis course, you can write it like this. Okay? Yeah, this is from your analysis course. Now, next thing I'm going to do is I'm going to once again apply property number 6 from the normal distribution notes. right? And so using property 6 here, property 6, we can see what you have there is minus 1 minus mu divided by 1 divided by root of n less than equal to standard normal less than equal to 1 minus mu divided by 1 over root of n. Mu not equal to 0. Right, and finally, we are done. I think finally this becomes phi at 1 minus mu divided by 1 over root of n minus phi at minus 1 minus mu divided by 1 over root of n. So this is the value for beta, and we have already found alpha, right? Okay, guys, so any questions? So we are done with the time, I think. So any questions, just feel free to contact me 24/7, all right? And also any questions about the exam, about our coursework, or anything else, you know, I'm usually in my office until 6 p.m. Monday to Friday, so you can just drop by and see me. There's no need to make an appointment, right? Okay? All right, guys, have a good weekend. I will send you an email shortly about quiz number 9. Yeah.
I don't understand how do we get from this step to this step. Why do we need to use the summate?
Because if it's less than equal to n,
yes,
and you can take values from 0 to n.
Yes.
That's what I'm trying to say here. Because if a Poisson variable is less than equal to n, sir, then it can take values from any value from 0 to n. Is that right?
Yes, but what do you need to add?
You need to add them together because it can be any of the values. It can be any of the values from 0 to n.
Yes.
So you need to add them together. Yeah, you need to add them together, man. Just think, like if Poisson is less than equal to 1,
yes,
it can be either 0 or 1. So you need to add the two probabilities together.
So here we are considering the probability of all the conditions that it's smaller than 1. So
Yeah. Yes. Yes. You're right. Yeah.
Thank you.
Come again. Come and see me in my office if it is not clear. You know where my office is?
No, where's the office?
2.223.
2.2 is the answer building.
Yeah.
Sure.
Yeah. You got a question?
Yes, I have a question about example 3.
Example 3? Yeah, this one, yeah. This is example 3. Yeah, what about it?
Maybe example 2. I don't know.
Example 2, this one, yeah.
I don't know how to convert this into this.
This one into this?
Yeah, this one into this.
Yeah, because if the probability is less than equal to n, it can take any value from 0 to n.
Yeah.
Yeah, that's what I have written here. This is what I have written here.
But if r equals to 0, it will be equal to 0. You
Yeah.
mean the Poisson distribution equals to 0.
Yeah, Poisson can take any value from 0 to infinity. Yeah, Poisson can be, can take value 0, yeah. Yeah. When you know that, I thought you know that from probability 1. Poisson can take the value 0, yeah. You have a question too?
I don't understand how to compare this to this.
Yeah, that's what you should have learned this in probability 1. If you have IID Poisson, then the sum is also Poisson. So instead of lambda, it should be lambda n.
Right.
Yeah. Ma'am, you have a question?
At the beginning, you said there was some non-examinable topics.
Yeah.
I missed it.
Yeah, all right. Those are two sample tests, two sample confidence intervals, and normal approximation.
Two sample hypothesis testing.
Yeah, two samples.
Confidence intervals.
Yeah, and normal approximation and continuity correction.
Normal approximation is
What was the
the
last one? Sorry.
Continuity correction. Continuity correction.
Thank
We
you.
didn't learn that in the class. So
We didn't.
we did not learn normal approximation in the class.
normal approximation is just from binomial and other
Yeah. It's
discrete distributions to normal distribution. Right?
that's right. Yeah.
Did we learn the continuity?
No, we did not learn that either.
Also, you know the coursework?
Yeah.
Do we get any marks for presentation or does it not matter?
No presentation. It's just the content.
So that you could do it on handwrite it and scan it,
Yeah, you can do it. Yeah, like that too.
or
But it's easy